Hello.
Thank you for coming to hear my presentation. Let's start my presentation. As you can see on the screen, the project consisted of one mentor, one project leader, and 5 mentees. Let me introduce myself now. I'm Inseo An, a third grade student at Korea Digital Media High School. Currently, I work as a researcher at NK. I am also actively participate CTF as a superguesser. If you have any question about the presentation, please feel free to email me.
I'm Jemin Min, a student at Korea University Sejong. Currently, I work as researcher at a company called NK.
This is the agenda for this presentation. First, I will introduce what is electron and how to analyze it. Then I will share the attack surface based on the characteristics of the apps with real examples. And finally, conclude the presentation. Now, I will introduce what Electron is. Electron is a framework that embeds Node.js and Chromium to facilitate the development of desktop application using web technologies. Similar to modern web browsers, Electron consists of one main process and several render processes. This presentation is not focused on the structure of Electron, so I'll briefly explain the concept. First, the main process runs in a Node.js environment and responsible for creating and managing application windows. If it interacts with the user's operating system to allow Electron to function beyond simply being a web wrapper. Now let's discuss the render process. The render process is primarily responsible for rendering web contents. It is managed through a main process and can communicate with the main process through inter-process communication called IPC. Let's talk more about the communication between the main process and render process. When the render process sends an IPC request to use the features in main process, the main process receives a request and executes functions such as menu and dialogues. At this point, you can see that the structure of a render process is a bit unique because the render process can import specific modules directly to web contents for security reasons. Instead, use a preload script. Now I will explain the security options. First, let's talk about node integration. These options controls whether node integration. By default, this option is disabled. And if you enable it, the render process can access to Node.js. Enabling this option can potentially lead to remote code execution to vulnerability like XSS. Next is context isolation. This option determines whether the separate JavaScript context, running preload script, and internal logic from the JavaScript context running web content. Default is enabled. If disabled, preload script, Electron internal logic, and web contents all run within the same JavaScript context. This enables attacks such as prototype pollution and so on. Next, I will introduce some research related to Electron. First, Black Hat introduced an exploit method based on the activation of Electron's security options, and HitCon, the result of the study based on Markdown app, were presented. All of the apps you see here are Electron applications, and now we are going to announce how we analyze and attack these applications. First, within Electron application, there is a file called app.asar, which can be unpacked using an npm package called asar unpacker to get applications code. However, code is often challenging to analyze due to technique like obfuscation being applied. Then now let me introduce you to technique for extracting useful information from the codes. First, find the part that handling the URL. For Electron, the ability to open external page or apps is usually implemented through a function called openExternal. This function is responsible for opening URL to default setting on user's PC. If users deliver a specific web page URL as an argument, functions to open URL to default browsers on user's PC. If the executable file path comes in as an argument, it will run the executable file. Therefore, these implementations usually have a sanitization process for URL. The second is to make sure that the security options are set up properly. I'll give you an example of the options that I described in the previous slides. As you can see on the screen, if node integration is set to true, the renderer process can also run the Node.js modules, it making it easy to trigger the remote code execution with only the accesses. And if context isolation is set to first, even a function with sanitization logic can disable sanitization through prototype pollution attacks. Now I'm going to talk about dynamic analysis. Exploit Electron application requires accesses in most cases. However, these access vulnerabilities are so difficult to find statically in the code obtained from app.asar. And app.asar does not contain the source code of the web page loaded by application, and then requires dynamic analysis. Because Electron uses Chromium, the developer tools allow for easier dynamic analysis. Dynamic analysis is aimed to trying as many things as possible and finding vulnerabilities that allow you to arbitrarily invoke the features of an Electron, such as accesses. Now I'm going to explain the technique that we have discovered in the course of project to bypass protection. First, manipulate the app.asar file size. If you look at the screen, the file on the left is normal size, but the pictures on the right has abnormal size. I explained earlier that you can unpack an app.asar file using an npm module called asar unpacker. However, if the size of the file is manipulated, it becomes impossible to get source code to asar unpacker. We solved this in a simple yet effective way. We created a script file to brute force the app.asar file size until we obtained the correct size. We provide an abnormal file to the script as an argument and tried to change and decompress it by increasing the size about 1000 until the correct file was extracted. Using this method, we were able to overcome all the challenges we encountered while analyzing the apps. And then the next thing is prohibit use of developer tools. It was impossible to open the developer tools in quite a few apps that did the analysis. There may be various reasons for this, but most of them were assumed to have been blocked for security reasons. I was looking at a number of ways to solve this problem, and I found a very useful tool. It's a tool called Debugatron that directly opens the app's developer tools. This allowed us to open developer tools in almost every app. Now I'm going to provide you with an example of common surface and real vulnerabilities in key function by category. First, let's focus on collaboration applications. In collaboration apps, you will often find features related to permission management, user profile, and communication. The currently screen displays example of user profile and permission management. You can attempt to trigger access in a field like name, where users typically input their information. By exploiting the fact that Electron typically uses open external to open links, you can insert a scheme such as SMB or file instead of the typical HTTP schemes, potentially leading to vulnerabilities like the file execution or arbitrary file download. While this may not be a high-level vulnerabilities on its own, when combined with other vulnerabilities, it can escalate to high-level vulnerability. We will explore an example of this later. And to learn a little bit more about XSS trigger point, it's good to try recklessly, but it's also a great choice to find relatively negligent factors such as when fields like name and role are used indirectly, as you can see on the screen. Next, let's discuss the chat-related aspect. Firstly, the user input section serves as a common attack vectors for XSS. If Electron has implemented convenience features like auto-run after download, you can potentially use them as an attack vector. Now I will explain a vector where we discovered many XSS while analyzing the chat features. We found numerous XSS vulnerabilities in the emoticon transfer functions. Typically, emoticon requests are structured as follows. If the structure is altered as shown below, and user input is not handled properly, it can lead to XSS vulnerabilities. The follow section covers extension vulnerabilities. Generally, extension can be categorized into those directly provided by app developers and those directly provided by ordinary users. And extensions directly provided by app developers acknowledge vulnerability report. Extensions can be viewed as a good attack vector because it is less secure than application. The screen shows an example of calendar extension and attack surface. Now I'm going to give you an example of real vulnerabilities. This vulnerability was reported in 2022 by CSRF and received $1,000 as a bounty in 2023. First, this app has a custom scheme implemented as an Electron. If you look at all the options in this scheme, you can see that course is allowed. But there is no restriction on this scheme, which creates a vulnerability. In this app, we are able to embed the links we want to extension. First, embed the attacker site for an attack. The attacker site uses a custom scheme implemented as an Electron to send a request to the app's API. Originally, it should not be allowed, so it is normal. But the allow course option in the custom scheme not only the request successfully, but also sends the user's cookie. Therefore, if you embed the attacker's page and then share it with victims, attackers can perform any request with the permission of the victim being shared. Next is IDE. Local file access and syntax highlighting is IDE's main function. Different vulnerabilities can occur depending on how to access local file in application. Let's look at an example of vulnerability caused by incorrecting local file access. We found these vulnerabilities last year while working on project, but we failed to report it because it was patched while we were working on a vulnerability report. First, when access a file from VS Code, we approach it as follows. We attempt path traversal and successfully exploit it. Noting that the path was exposed as is without any security measures. As an example, we confirmed that by manipulating the URL in the section responsible for file access as follows, it's fast to load any local file. While these vulnerabilities may not pose a significant risk on its own, when combined with other vulnerabilities like XSS, it can escalate into a several vulnerability, potentially allowing attackers to steal arbitrary files from users. Next is extension. IDE also supports a variety of extensions, which, as mentioned earlier, these can serve as potentially attack vectors due to their relatively lower security. The screen displays an example of an extension related to Git. Now let me show you the real vulnerabilities of extension. This vulnerability is a remote code execution caused by a logic bug in Kinland, which is a very dangerous vulnerability because it can be triggered even in a restricted mode that typically prevent extensions execution in Visual Studio Code. The vulnerability exploits the fact that the extensions run immediately if there is an FS monitor in the config file under the Git directory. Let's see the demo. Finally, the Note application. Note application typically serves Markdown, so there are numerous attack vectors to consider. One area that often contains many vulnerabilities is the embed section. And being able to embed arbitrary site is also a significant attack vector. This is because if you can embed an attacker site and the Electron version is low, you can potentially use a Chromium exploit to archive remote code execution and also can do many things. I'm going to show you a real example of exploiting 4 vulnerabilities to achieve remote code execution in an app that allowed arbitrary embedding. This vulnerability was reported last year and rewarded $1,800 as a bounty. First, let me explain the access vulnerability. This app used iframe to embed specific links. Due to the shared embedding functions used by other internal logic, it includes an option vulnerable to iframe's sandbox properties. This option is called allow-time navigation by user interaction. And if enabled, it allows changing the URL of the top page when there's user interaction like dragging or clicking. Even if the content is loaded within an iframe. By utilizing this, if you can redirect the location of the top page to the attacker side and run arbitrary script, can use the various Electron functions that the app has implemented that are only available on the top. Now I'm going to demonstrate how to achieve file execution using the XSS vulnerability I mentioned earlier. First, there is an API in the top page called OpenURL, which sanitizes the URL provided as an argument. And open external it with the specified conditions. At first glance, it may seem like an idle code, but there's a vulnerability. The context isolation option this app is set to first. Because this option is first, prototype pollution is possible and sanitization logic can be bypassed. If you follow the include function as shown on the screen, even if a malicious URL is provided, it always listens through, allowing you to open a URL with the desired scheme. This makes it possible to execute arbitrary file and SMB connection. I mentioned earlier that attackers need user interaction to trigger XSS at the top. Let me explain how we induced it. We were considering ways to induce user interaction and discovered the app was using a specific modules in an older version, which allowed for CSS injection. Using this, we decided to mimic the app's error page. We are able to naturally induce user interaction as follows. Now, let me explain how we achieve remote code execution. We used a method that involved executing a PowerShell script. First, writing malicious script that bypass Windows Defender, and creating web file that run the PowerShell script. Finally, saving them to the attacker server, and if the victim downloads and executes the two files, attackers can get victim share. If we type into the attacker's website code and explain it in detail. We first the sanitization by using prototype. We first bypass the sanitization by using prototype pollution to execute the file. Subsequently, we download the two files mentioned earlier from the attacker server. Since there is to be a path to run a file, we obtain the path of the download file, the applications implemented at path. By running the download file for the final time, we can successfully get a share. In summary, we induce user interaction using the error page mentioned earlier. If user interaction occurs, we change the URL of the top page to the attacker side and execute the code described in the previous slide. From now on, I'll explain what we have gained through the project. We reported 10 remote code execution cases, 2 local file leak, and 1 CSRF, 1 information disclosure. In addition to vulnerabilities, I was able to improve my ability to proceed with projects, such as role distribution and result organization. And I could feel the actual security industry atmosphere in the process, informing multiple vendors of vulnerabilities and adjusting bounties. I brought some themes for those who plan to work on Electron themed project. First is static code analyzer is based on the fact that the source code of Electron is white box. So it may not be easy due to obfuscation, but it is also meaningful to create a potential vulnerability scanner or an analyzer that companies can use before distributing their apps. And the new patterns progress that I did earlier and disclosed anywhere. Finally, find vulnerabilities in the Electron framework itself. If you find the vulnerabilities in the Electron framework, it will have a high risk impact. That's the end of the presentation. Thank you for listening to the long time.